In this video, we're going to take a look at rate law problems in the chemical kinetics unit, and we'll use this question to introduce the topic. We're given a chemical reaction, in this case between nitrogen monoxide, NO, and oxygen, O2, in which they react and form nitrogen dioxide, NO2. The balanced equation shows 2 moles of NO reacting with 1 mole of oxygen to make 2 moles of NO2. The reaction was studied at a very high temperature, at 660 Kelvin, and 3 trials were done. Notice that in the 3 trials, the rate of disappearance of nitrogen monoxide was measured in moles per liter per second, and they were done by changing different concentrations of NO and O2. So in trial 1, you had 0.010 moles per liter NO initially. The little 0 up here beside the NO in square brackets means the initial concentration of NO, and the initial oxygen concentration, let's say little 0 there means the same thing, was 0.010 moles per liter. The rate was measured, and here it is here, 2.5 times 10 to the minus 5 moles per liter per second. And that was the rate at which NO was disappearing in the reaction. In the second trial, you used a higher concentration of NO while you kept the initial concentration of oxygen the same as it was in trial 1, and you saw that the rate was higher, 1 times 10 to the minus 4 moles per liter per second. In the third trial, we used the same initial concentration of NO as trial 1, but we used a higher oxygen concentration, and compared to trial 1, the rate is higher again. From this information, this is typical information for what's called the method of initial rates. That's what we're going to use here, the method of initial rates, because you'll notice in the table we were given initial concentrations and we're measuring the initial rate of disappearance of NO. So it's called the method of initial rates. We're going to determine something called the rate law for the reaction. And within the rate law, we'll be able to see things like the order for each of the reactants, the order for NO and the order for O2, and we'll calculate what's called the rate constant. Part D and E here will then have us use that rate law. Actually, Part D will use the rate law to calculate the rate under different conditions. And then finally in Part E, we'll examine trial 2 in the table, and we'll see how the rate there relates to rate measured in different ways. So let's jump in, and we're going to find the rate law. Now a rate law is just a mathematical statement that describes how the reaction rate depends on the concentration of reactants. From our factors that affect rates, we remember that temperature affects the rate of a reaction, surface area if there's solids involved, catalysts can also affect rate, but concentration of reactants is a major factor that affects rates. In our balanced equation above, we notice that the reactants were nitrogen monoxide and oxygen. Those are the reactants. So their concentrations affect the rate of the reaction. That's why our data table shows us concentrations of NO and concentrations of O2, and then they're changing them, how that affected the rates over here. So we're going to look at the effect of concentration of those reactants on the rates. Since there were just the 2 reactants, we can write a rate law that looks basically like this. Rate equals a constant, which we'll call a rate constant, times the concentration of the first reactant raised to some unknown power x, and we're going to find x, times the concentration of the other reactant, oxygen, raised to some unknown power y. Now this entire statement is referred to as the rate law. The statement rate equals k times NO to the x times O2 to the y is the rate law. Within the rate law, the exponents here, x and y, are technically called the orders of the reaction. So x is the order with respect to NO concentration, the way I've written that. Y is the order with respect to oxygen. Now if we were to add them together, X plus Y, we would then have what's called the overall order of the reaction. So for example, if we find out that X is a 1, then we would say that the NO is first order. If we find out that Y is a 2, then we'd say that the oxygen is second order, and then the overall order of this reaction would be 1 plus 2. It would be third order overall. Within that rate law, there's also that little K, and that's going to be called the rate constant. The rate constant is constant only at a given temperature. And at a higher level of introductory chemistry, you'd study the relationship between rate constants and temperatures. For us, we'll simply see that in most questions it should tell us that the reaction was done at some temperature. So in this question it said 660 Kelvin was the temperature, and then in part C it says calculate the rate constant at 660 Kelvin. So the rate constant is calculated at the temperature in which the reaction was done. So our job in this question, part A, said to determine the order for each reactant. So we're going to find out what X and Y are equal to. Part B says write the rate law. Once we know those exponents, those orders, we can just rewrite this statement and replace X and Y with the numbers. And then part C, calculate the rate constant. We'll calculate the value of K in this rate law, and then we'll use the rate law to calculate the rate when we know K as well as the concentrations of NO and oxygen in part D. So let's jump in, and we're going to need to refer to our data table. We're going to refer to trials 1, 2, and 3. Okay? And what I'm going to do is, because we have three unknowns, we have an X, we have a Y, and we have a rate constant K, we need to have 3 trials minimum to solve for all 3 of those variables. What we're going to do is basically set up the rate law twice and divide it. And in dividing, we're going to see things cancel, and that will let us solve for one of the variables. So let's jump in. I'm going to start by finding X, and it's arbitrary. You could also have found Y. But let's find X, and just remember what that is. X is the order with respect to the nitrogen monoxide. Okay? Now, how will I find X? Well, what I want to do is look at my data table, and I want to identify 2 trials where the NO, that was the order for X, goes with NO here. It's matched together with NO. We want to find 2 trials where NO is changing, but where the oxygen concentration is not changing. So looking at the numbers, trials 1 and 2, the NO changes here, while the oxygen does not change. Therefore, any change in the rate that happens must be because of the NO, and therefore we'll be able to use the change in rates to figure out what X is equal to. So let's use trials 1 and 2. Use trials 1 and 2 where concentration of NO changes, but the oxygen concentration is constant. And again, that's because now any change in rate would be because of the change in the NO. Now look what I'm going to do. Looking back at the table, we notice that trial 2's rate is larger than trial 1 rate. 10 to the minus 4 is bigger than 10 to the minus 5. So since trial 2 has the larger rate, I'm going to find X by taking the rate for trial 2 and divide by the rate for trial 1. I like to put the larger rate on top, and that's just because when I divide, I'm now going to get a number greater than 1. If you divide 2 numbers like 4 divided by 2, your answer is a nice number 2. If you reverse that and divide 2 divided by 4, you'll get a fraction. You'll get 1/2. There's nothing wrong with fractions, but most people prefer dealing with whole numbers. So taking the rate for trial 2, and look in your own data table and make sure you agree these numbers are correct. So we have 1.0 times 10 to the minus 4 moles per liter per second, divided by the rate for trial 1, which was 2.5 times 10 to the minus 5 moles per liter per second. Now before I just divide those things, look what I'm going to do here. We said that in our rate law that the rate was equal to a constant times NO's concentration to the power of X times oxygen's concentration to the power of Y. So let's take that logic, and over here in this statement, rate number 2 had to equal 1 times 10 to the minus 4, but that has to equal this constant times concentration of NO to the power of X times the concentration of O2 to the power of Y. In the same way, on the denominator, rate 1 also has to equal K times the concentration of NO there to the power of X times the concentration of O2 in trial 1 to the power of Y. And now, to get the numbers for those brackets, just look back at your data table. In trial 2, the concentration of NO2 was 0.02 and O2 was 0.01. In trial 1, they were both 0.01s. So let's put those numbers into these brackets, and be sure you put trial 2's concentrations on top to match with rate 2. So 0.020 was the concentration of NO, 0.010 was the concentration of oxygen, and on the bottom 0.010 was the concentration of NO in trial 1, and 0.010 was the concentration of oxygen in trial 1. Now, if you grab your calculator and divide the two rates, 1 times 10 to the minus 4 divided by 2.5 times 10 to the minus 5, you should find that that is equal to 4. Equals, and now look at by dividing like this, look what happens. Your rate constants will cancel. K divided by K is just 1. And then because the concentration of oxygen was not changing, we can also cancel 0.01 to the power of Y on top and 0.01 to the power of Y on the bottom. What that leaves us is 0.02 to the power of X divided by 0.01 to the power of X. Now before I evaluate that, just a quick word about powers. In math class you've learned several rules for powers, things like 2 to the 3 times 2 to the 2 is 2 to the 5, you know, to add the exponents when you multiply powers with the same base, or 10 to the power of 5 divided by 10 to the power of 4 is 10 to the power of 1. You know that when you divide powers with the same base, you just keep the base and subtract their exponents. 5 minus 4 is 1. A rule, though, that you probably haven't learned is the rule we're going to use here. What happens if you take 10 to the power of 4 and you divide by 10 to the power of 1? Sorry, 2 to the power of 4. Let's do that. My mistake. 10 to the 4 divided by 2 to the 4. Well, 10 to the 4 means 10 times 10 times 10 times 10, and 2 to the 4 is 2 times 2 times 2 times 2. And notice now we could group this as 10 divided by 2 times 10 divided by 2 times 10 divided by 2, etc., which means that that has to equal 4 or 5. 10 divided by 2 is 5, times 5 times 5 times 5, which is 5 to the power of 4. So what we're basically saying is 10 to the 4 divided by 2 to the 4 is 5 to the 4. And here's a rule you probably haven't seen before. When you divide powers with the different bases, but the same exponents, you simply divide the bases. 10 divided by 2 is 5, while you keep the exponent the same. Using that logic, let's look back here. We have 0.02 to the x divided by 0.01 to the x. So 0.02 divided by 0.01 is 2. And then we still have to say to the power of x. Now in your head, 2 to what power gives you 4? If you start thinking, you'll realize that 2 to the power of 0 is 1, so that's not going to work. 2 to the power of 1 is 2, that's still not going to work. 2 to the power of 2 is 4, and that's the one we want. And of course, 2 to the 3 is 8, and we can keep playing that game, but this is the one that we want. 2 to the power of x equals 4, therefore x is equal to 2, because 2 squared is 4. So we just found x, the order with respect to NO. Let's do the same thing now a little bit faster, and we'll find y. This was the order with respect to oxygen. Now look back at your data table and decide which 2 trials you're going to want to use to do this. In the data table, it would be best if we could find 2 trials where the oxygen concentration is now changing, but where the NO concentration is held constant. So that looks like trial 1 and trial 3, right? The oxygen there changed, but the NO did not change. And when we look at those 2 trials, we notice that rate number 3 is larger than rate number 1. So let's divide rate 3 divided by rate 1. So we're going to use trials 1 and 3, where the oxygen concentration changes, but the other concentration, the NO concentration, is constant. Now just a little word about that. When we found x, we needed to use that reasoning. We needed to use trials 1 and 2 because the NO was changing there and oxygen was constant. Technically speaking, now that we know that x is a 2, we've already determined that, we really don't have to keep trials, we don't have to keep the NO constant. We could use 2 trials to find the second order here when the NO was changing, because we actually know what its order was. And now we're not going to see that here, but we'll use this same logic, because if you do have a choice, it is easier to do what we're doing here, to use 2 trials where the NO is being held constant so that it cancels out as we divide. So we're going to take rate number 3 and we're going to divide by rate number 1. Okay, we're using the larger rate on top. And again, that's not the larger rate because it's rate 3 versus rate 1. That's not what I'm looking at. I'm actually looking at the numbers in the table, right? It happens that in trial 3, its rate was larger than the rate in trial 1, but it didn't have to be, and it's possible that the table would have had rate 1 being larger than rate 3, okay? So let's grab the numbers from the table. Trial 3's rate was 5.0 times 10 to the minus 5 moles per liter per second, divided by the rate for trial 1, 2.5 times 10 to the minus 5 moles per liter per second. And let's do that same little trick, equals K times something. Now, I'm not going to put to the power of x here, because we've already determined that x is a 2, so I'm going to put to the power of 2, times the concentration of oxygen to the power of y. And on the bottom, K times the NO concentration squared times the O2 concentration to the power of y. Look back at the table for trial 3 and put the 2 concentrations on the top, and in trial 1 put the 2 concentrations here on the bottom. For trial 3 we have 0.010 squared and 0.020 to the power of y, and in trial 1 we have 0.010 squared and 0.010 to the power of y. Dividing 5 times 10 to the minus 5 divided by 2.5 times 10 to the minus 5 is 2. And so that equals, the k's cancel. 0.01 squared divided by 0.01 squared cancels. And we're left with 0.02 to the y divided by 0.01 to the y, which will equal, using the same logic we used a minute ago, 2 to the power of y. So 2 to the power of y equals 2. Therefore, we're going to want to use this guy. The y must have been a 1, because 2 to the power of 1 is 2. So we can say, therefore, y equals 1. Okay, we've just determined the order with respect to NO. We found that it was a 2, so NO is second order, and the O2's order is a 1, so the oxygen is first order. That was part A of the question. Part B of the question said to write the rate law, the rate equation, it called it. So let's write the rate law. The rate equals K times concentration of NO squared times O2 to the power of 1. If it's a 1, you don't need to put the exponent or the order in. Part C was to calculate the rate constant at 660 Kelvin. If we take the rate law and just rearrange it to solve for K, to get K by itself, you would divide both sides by these concentrations. And so K would equal the rate divided by the concentration of NO squared times the O2 concentration. Now, if this data was real, if this were a real experiment and we had 3 trials, we would calculate K 3 times for trial 1, trial 2, and trial 3, and then we would take an average. This data, I hope you got a good sense for it, was fixed. It worked out perfectly that 2 squared was 4 and 2 to the 1 was 2. Therefore, I'm not going to waste time and calculate K 3 times. I'm just going to pick one of the 3 trials, and it does not matter which. I'll use the first trial. So I'm going to calculate K1, which is the rate constant in trial 1 of the experiment, equals, and I'm going to be careful now to put my units in. The rate there was 2.5 times 10 to the minus 5. Now it says moles per liter per second. Moles per liter per second. Moles per liter is molarity. So really, this is molarity per second, which we could write like this, molarity per second. And that's how I'm going to put it in here, just to make it a little bit easier. Molarity per second. Divided by the concentration of NO2 is 0.010 molarity, moles per liter, and we have to square that, times the concentration of oxygen, which was also 0.010 molarity, and that's just to the power of 1. So grabbing my calculator, I'm going to take my calculator here, and I'm going to enter 2.5 times 10 to the power of negative 5, divided by 0.01 squared, and then I'm going to divide again by 0.01. So I'm dividing by 0.01 squared to take care of the first part of the denominator, and then I'm dividing again by 0.01, and I get 25. Another way to do that would have been to type 2.5 times 10 to the minus 5 divided by, and then use brackets, 0.01 squared, and if you're going to use brackets, then now it would be times 0.01, and close the brackets, equals the same answer, 25. So my answer numerically is 25. But rate constants also have to have units with them. So let's look at the units here. On the top, we have just molarity per second. Okay, those are the units for rate. On the bottom, we have molarity squared times a molarity. If you were in grade 9 and you heard x squared times x, you should think that that means x to the power of 3. So in the same way here, molarity squared times molarity is molarity cubed. And now on the top we have a molarity to the 1, on the bottom we have a molarity to the 3, and when you divide powers with the same base, you subtract the exponents. So 1 take away 3 is negative 2. So this thing's units are molarity to the minus 2, and then we still have the per second. Okay? So again, on the top we had just a molarity per second. On the bottom we have molarity squared times molarity, which is molarity cubed, and then 1 take away 3, we'll have m to the minus 2, and then the per second is also there. So there's the value of the rate constant with its units at 660 Kelvin, the temperature in which the experiment was done. Part D told us to calculate the rate of the reaction when the concentration of NO was 0.015 molarity and the concentration of oxygen was 0.0050 molarity. It says, what's the rate of the reaction? Well, our rate law says that rate equals, and instead of a K, I can just put this number now. So rate equals 25 times concentration of NO squared times oxygen equals 25 times 0.015 squared times 0.0050. Now you'll notice I'm being a little lazy not putting the units in here, but the units that I'm going to get for the rate will be the same units that the rate had in the data table. So I don't have to prove that to myself. I'm just going to use the same units for rate over here, molarity per second. That will be the units down here. So with your calculator, 25 times 0.015 squared times 0.005, I get 2.8 times 10 to the minus 5 molarity per second. Those are the units for the rate. It's the same units that were in the data table, moles per liter per second. And then finally, in Part E, the question said, in trial 2, what was the rate at which the oxygen was disappearing, and what was the rate at which the NO2 was appearing? If we look back at trial 2 here, we'll notice that the rate at which the NO was disappearing was 1 times 10 to the minus 4 moles per liter. So that's the rate at which NO was disappearing. How fast was the oxygen disappearing? To figure that out, just look at your balanced equation. 2 NOs plus 1 O2 makes 2 NO2s. So in trial 2, okay, looking at my data table, the change in concentration of NO over change in time was 1 times 10 to the minus 4 moles per liter per second. And I'm going to throw a negative sign in front of that rate symbol because the NO was a reactant, its concentration was decreasing, so the change in concentration would have been negative. By putting a negative sign out front, it makes the rate positive like we see here. The question was, what was the change in oxygen's concentration? What was its rate of change? So negative delta O2 over delta T, the rate at which oxygen was disappearing, what would it equal? The key is to look at the coefficients. Every time you had 2 NOs disappear, only 1 oxygen disappeared. So the oxygen is not disappearing as fast as the NO. In fact, it's going to disappear half as fast, right? 1 to 2 is the ratio. So if we just take 1/2 of 1.0 times 10 to the minus 4, we'll get the answer to that question, and it's going to be 5.0 times 10 to the minus 5 molarity per second. So that's the rate at which the oxygen was disappearing, delta oxygen over delta T, the rate at which it was changing. Again, the negative sign is there simply because the oxygen was a reactant. Its change in concentration is negative. By putting a negative in front, it will make the rate positive that we see over here. What about the NO2? What was the change in concentration of NO2 over change in time? What was the rate at which it was appearing? Notice because the NO2 is a product, I'm not going to put a negative sign out front because its change in concentration is already positive, so I don't need to throw a negative in front of that. Well, looking at the equation, there are 2 NO2s that appear every time 2 NOs disappear. So the rate at which the NO2 appears is the same as the rate at which the NO disappeared because the ratio is just 2 to 2. So we can say that the rate of NO2 changing over time was the same as the rate of NO, so it would be 1.0 times 10 to the minus 4 molarity per second. So the key is simply to look at the balanced equation to get the ratios in order to compare the rates at which things are appearing and disappearing. So there is a typical kind of detailed explanation of how to do a rate law problem. The rest of the problems on the sheet are very similar, and this is a guaranteed problem on a kinetics test, as well as highly likely to show up on a final exam for grade 12 chemistry.